Hola. We're back. We are going to talk about the basicity of amines. All right, so to kind of start the process, first I want to remind you about ammonium cation, which is a weak acid. It's the conjugate acid of ammonia, and the pK value of ammonium is 9.25. All that we have around the nitrogen is just hydrogens. So basically, there's nothing else going on besides that. But this is going to be a reference value that will change depending on what kind of substitution we are applying to the nitrogen. So for instance, if we were to replace one of those hydrogens or protons with methyl, we actually see an increase in the pKa. And what this means is that the conjugate base of these molecules, so instead of having methylammonium cation, if we just have methylamine, what this will tell us is that methylamine is more basic than ammonia. Okay, so that's what this is saying. And I'm going to explain why that is momentarily. If you kind of follow the trends just a little bit further, so replace a second proton with methyl, you see further increase of the pKa, meaning that you are increasing the basicity of the conjugate base of these ammonium cations. So the reason why that's happening is because in the case of ammonia, right, so the conjugate base of ammonium, all you have is hydrogens bound to nitrogen. And yes, you do have the lone pair, which is what makes this thing partly basic, but you don't have any additional contributions to the electron density around that nitrogen, at least not in ammonia, right? So what we would say is that, yeah, there's no hyperconjugation going on here, and I'm going to show you what that means momentarily. When you look, though, at the methyl derivatives or the alkyl derivatives of ammonia, which are amines, now what happens is that you have these bonds, right, like the CH bonds, that due to the free rotation about this carbon nitrogen single bond, they are kind of lining up parallel towards the lone pair of electrons. And due to that interaction, you actually have some of the electron density of the CH bonds being applied onto the lone pair of your amine fragment. And that basically makes the electron density go up around nitrogen, which increases the basicity. So you could argue the same thing is going to happen to a greater extent if you now add a second alkyl chain to your nitrogen. So, if we had hyperconjugation to begin with, well, now having additional hyperconjugation is only going to augment the effect of increasing the basicity. So that's the idea right here. Now, at the core of this, if you really want to dig into what exactly hyperconjugation stands for, we will have to talk about molecular orbitals, which I did debate about putting in this slide, but I decided to just kind of keep that out just for the sake of simplicity. But if you're wondering about it, yes, molecular orbitals are involved. All right, now increasing the number of alkyls on nitrogen increases the basicity, but also changing the type of substituent, the type of alkyl that you have bound to nitrogen also has an effect. For instance, generally speaking, changing methyl to ethyl, and you can see it here on the middle portion of the slide more easily, changing methyl to ethyl tends to also increase the pKa. And the reason for that is that some of the sterics also impart a lot more emphasis on dumping electrons onto your nitrogen lone pair, and increasing that basicity. And you can kind of extrapolate that from methyl to ethyl, all the way to isopropyl. If you increase the chain in that regard, then you will find the basicity of isopropyl is higher than that of ethyl or methyl, because the extra set of bonds, the extra steric bulk, definitely helps to dump more electron density onto your nitrogen lone pair. And needless to say, if you have one isopropyl, two isopropyls, also kind of help out. You increase the basicity, somewhat. All right, now kind of changing gears a little bit. If instead of having a regular alkyl bound to nitrogen, we have an aromatic component directly bound to nitrogen, now we see a significant drop in the pKa. This is actually almost as acidic as a carboxylic acid. Not quite, but very close to it. And the reason for that is because when you consider what's going on with aniline, the conjugate base of the acid that we just looked at, well, you have basically the option for resonance. The lone pair of nitrogen can engage with the carbon of benzene to basically create a resonance structure in which the nitrogen now develops a positive charge. And because of the development of that positive charge, you decrease the electron density about the NH bond, and you make the proton a lot more like a naked proton as opposed to being part of a bond, which is the same thing as saying that the acidity increases, right? And this is only one of the resonance structures you can have. You have another three that will still give you nitrogen with a positive charge. So that's part of the reason, and you could maybe even argue that that is the main reason why the pK of anilinium is so much lower. All right, now slightly differently, but if we look at a pyridine derivative right here, and I'm going to show you the pK of this momentarily, but if we have another moiety, so here we have an additional amine, this is known as dimethyl aminopyridine, and it's known as DMAP for short. It's a very useful base which you can ultimately use for just deprotonations, acid-base chemistry in various reactions. So yeah, it's very well utilized in that respect. All right, so now for this to make sense, first I have to show you what's going on with pyridine itself. So pyridine, if you have it protonated, the pK of this conjugate acid is 5.2. So it's not as low as anilinium, um, because you don't have as great access to all the resonance structures that anilinium has, but you still are part of an sp2 system right here, the aromatic system. So you lower the pK as a result of that. All right, now if instead of just having pyridine, you have this additional amino group here in the para position, um, this can donate its electrons towards the benzene, kind of like what we did with aniline, and these electrons can definitely shuffle around until you get the electrons to pretty much end up dumped onto the nitrogen that's part of the ring. And what you can see from this specific resonance structure is that yes, we are creating a positive charge, but the positive charge is happening on the nitrogen that doesn't have any hydrogens, whereas the negative charge here, which appears on the nitrogen on top, that's the nitrogen that's going to have the extra nitrogen, excuse me, the extra hydrogen attached to it. So the fact that this ends up with a negative charge means that you're going to hold on to your proton a lot more tightly. And so the end result is that yes, the pKa of DMAP is higher than the pK of pyridine itself, right? So we have those resonance effects, at play. All right, now here I've been saving this on purpose right up until now. So I mentioned to you that if you add one alkyl, like one methyl, and then you go to two methyls, the pK increases. And you would think the same thing will happen if we increase from two methyls to three methyls. But it turns out to be the case that actually the pK drops down. Now it's at 9.8. And you might think, is this just an anomaly? Or, is there something else at bay? Uh, but yeah, so increasing the hyperconjugation gives you lower basicity. Something doesn't sound right here. And what ends up happening is that when you go from being a secondary amine, meaning two alkyl connections to nitrogen, to now becoming a tertiary amine, having three alkyl connections to nitrogen, you go from having the ability to hydrogen bond to no longer being able to hydrogen bond, at least not with other tertiary amine molecules. Now, the reason why that's important to note is because if we were to take this kind of to the extreme, the interaction right here, hydrogen bonding interaction, is between the nitrogen lone pair, shown in blue, with the NH bond of the black amine. But if we were to take this interaction to the extreme, technically what that would mean is that you are attacking with a set of lone pairs the NH bond of the adjacent molecule, and those electrons technically are getting dumped onto the nitrogen of the bottom amine shown right here. So in the most extreme situation, what you're basically doing is taking a proton away from a partner or an adjacent molecule, and that adjacent molecule now has increased electron density on nitrogen as a result of that interaction. Now, during hydrogen bonding, you don't necessarily go all the way here, although in the pure amine solution there is an equilibrium. It's much lower than the equilibrium that water has for autoionization, but it does occur to some small extent. Uh, but even without it, just the act of hydrogen bonding has some of that electron density getting dumped onto the nitrogen that has a lone pair available to it. And that act alone increases the basicity of that nitrogen by increasing the electron density. So that's the main reason why going from a secondary amine to tertiary, there's a drop in the pKa. So it's very, very interesting that, those effects kind of take place. A little bit counterintuitive, but once you kind of like think about it, you're like, okay, I can see that being a thing. And it's not exclusive to trimethyl ammonium. If you look at triethyl ammonium and compare it to diethyl ammonium, you also have a decrease in the pKa. If you look at and it's kind of a random one now right now, but if you look at tertiary alkyl, you also have a drop in the pKa compared to your traditional dialkyls right here, right? Um, so this one happens to be called quinacridine. I just wanted to point it out just for your information more so than anything else. But we also have a derivative of quinacridine. That's the reason why I'm showing it right here. This one is called DAPCO. It's the formal name is diazo-bicyclo 2.2.2 octane. But you can see taking some of those letters and using it as an acronym, DAPCO, that kind of works out. So if you look at these two molecules, quinacridine and DAPCO, what you will notice right away is that the pK of the most basic nitrogen is still lower than the pK of just quinacridine by itself. And the reason for that is that quinacridine, it just has a bunch of carbons around, so there's really no additional factor that could be withdrawing electron density away from that NH bond. But in the case of DAPCO, which you should definitely pay attention to because you could be saving 15% or more on molecular insurance. All right, so DAPCO. Basically, from the point of view of the front nitrogen, the back nitrogen is attracting electron density towards itself, right? And it's kind of being felt throughout this entire ring. And because of that, now you're depleting electron density from the front nitrogen and in essence the NH bond. And both of those effects lower the pKa of the first and the second proton of DAPCO. So kind of a cool additional factor to take note of and consider. All right, so with that in mind, here I'm showing you again the list of the secondary ammonium salts, the list of the tertiary ammonium salts, and what I want to then pretty much call to your attention is the fact that guanidine, which I mentioned a little bit earlier, um, this fragment technically it's kind of like your secondary amines, right? You have two alkyl connections to nitrogen, two carbon connections to nitrogen, I should say, and then two H's. And that's kind of what you have right here. You have an NH2 with two connections to carbon. Um, and you can see that the pK of this thing is a lot higher, meaning that this fragment, the guanidine fragment, is a lot more basic than just your typical secondary amines. And the reason for this is simply because you have a bunch of extra nitrogens right next to a multiple bond. So you have the option for resonance taking place, kicking the electrons onto that nitrogen, making it negatively charged, right? And not just once, but technically twice, right? You have two NH2s that can affect the electron density of the top nitrogen right here. So you have a lot of electron density being pushed towards that nitrogen, making this nitrogen very, very basic. And it is one of the most basic nitrogens for most of the biomolecules that we're going to be talking about in the future. So, you should be aware of that. All right, and then as a last example, kind of looking at the tertiary ammonium salts, DBU, diazobicycloundecine, 7-undecine. This is a typical base used in organic synthesis, and if you look at it, you have three connections to carbon, only one NH, right? Very reminiscent of the tertiary ammonium salts up there, but this is also has a higher pKa than the counterparts, and the reason for that is the same reason that we saw for guanidine, and that's that you have a nitrogen um, next to the imine bond, so you can actually undergo resonance, entering this nitrogen here negatively charged. And so one thing I want you to kind of really notice is that out of those two nitrogens, there's only one that's actually very, very basic, and that will be the one where protonation will happen first, and it's the nitrogen here on the bottom, because that's the one that actually ends up with a negative charge. So you will have to use some resonance arguments to determine if molecules have multiple nitrogens, which is the nitrogen that's actually going to get it protonated if you react it with a proper acid. All right, so that's kind of the idea. And with that, we'll stop the video at this instance. We've already talked enough about basicity trends, but hopefully that gives you the full scope of how to kind of look at your molecules and assess, whether they are more basic or not. Okay, so with that said, I will catch you on the next video. Bye bye.